years of experience, intellect, and perfection in an operation. Our today's speaker has proved this to be true with his years of perseverance. Our today's speaker is Dr. Navin Velmurugan, who holds PhD in Mathematics and Control from Mainz Paris Tech. Dr. Naveen is a professional petroleum engineer with more than 6 years of academic training in drilling section of oil and gas industry. I feel elated as I say that he is an alumnus of 2010-2014 batch of BTech Petroleum Engineering PDPU. We are aware of the significance of controlling the pressure while drilling. The use of MPD systems to control the risk and cost of drilling wells that have narrow pressure limits by actively managing the wellbore pressure profile has become a common practice. Hence, we are back again with a session on Introduction to Managed Pressure Drilling Modeling. This webinar is going to be about modeling of MPD systems for automatic control of BHCP, and along with this, the talk will also present a brief introduction to the distributed dynamics and reservoir models. Regarding the session, I request all the participants to keep themselves muted to avoid any unnecessary disturbance during the session. So without any further ado, I would like to request Dr. Naveen to commence with the session. So please.
Thank you so much for the kind introduction and welcome you all for this webinar. Let me just try to share my screen first. Can you see my screen already?
Yes, sir, we can see.
Perfect. All right. So before we begin, I would like to thank Nehal especially to contact me and organize this particular webinar. And as the introducer mentioned, it is an introduction to the managed pressure drilling operations, and we will look at the modeling aspect of this particular problem. So I have planned for almost 20 to 30 minutes of talk. But I would say that I will stop the presentation briefly in between to address any of the questions that you may have. And then we can, go on and discuss further once I finish this talk. So just let me know if you have any questions in between or something like that. Okay, just for people who don't know what exactly I've been doing, I am an alumnus of PDPU. I graduated with the petroleum engineering degree and specialized in upstream, mainly in the exploration and production sector, batch of 2010 to 2014. And then I went on to do my master's at Norwegian University of Science and Technology in Norway, and I specialized further in drilling engineering. And recently, I earned my PhD degree in mathematics and control. During this project, I worked on modeling the hydraulics in the drilling systems and provide some automation and control algorithms for MPD system in particular. So I had the opportunity to work with a company called Kelda Drilling Controls. They are in Norway. They are a startup who are providing software solutions for automation of the MPD systems. So this is a small shout out to them. You can go and check out their website, kelda.no. They have nice products and simulators for managed pressure drilling systems. Follow their blog to understand what they are doing and to be updated of the new technology. So my PhD program was funded by the European Union, and it was a consortium of TUE in Eindhoven, Mean Paritech in Paris. That's where I graduated. And also Kelda was our industrial partner. So first we will look at a brief introduction to drilling, why pressure control is important, and how managed pressure drilling could address it. Then we will go on and see how to model such systems mathematically so that we can have an understanding of the dynamics that are occurring inside the wellbore. And then this is required to, how this can be used to design automation solutions for this particular application. Since I was told that you're all in the undergrads and have very, starting to have an understanding of drilling system, I thought I could go on from the very basics, right? As you know, drilling for an oil and gas well is a complex and safety critical, challenging operation. Firstly, we have the mechanical forces. At the drill bit, you have the torsional force that you apply to cut the rocks, and you also have the translational force to send the drill pipe down, and you have additional weight to facilitate this cutting process. In conventional drilling, you start drilling this, and then you go case a particular section of the wellbore, and then you drill ahead, and then you always have a particular section of the reservoir or the formation that is always open and can communicate with the reservoir, communicate with the wellbore, right? During this operation, what we also need is a circulation of particular engineered fluid called drilling mud. First of all, to remove all the cuttings that you drill out from the particular formation. Next, to maintain the pressure against the open section of the wellbore. And then there are other functions like lubrication, transmission of the hydraulic power from the surface to the bottom. But we will not, so there are multiple functions, but what we'll focus in this particular talk is how we could use drilling mud to maintain a particular pressure at the bottom of the wellbore, right? So the general flow of direction of this drilling mud is that you pump using a mud pump at the surface that goes down in the drill string, and then it experiences a pressure loss at the drill bit, and then it is circulated up through the annulus and then flows out at the surface. Now, when you look at the pressure aspect, so we have certain pressure gradients that we have to respect when you drill for a wellbore, right? Is there any question?
No, sir, please continue.
Okay. So here is a schematic of the pressure gradients that we generally have as we go down deeper in the underground surface. The first one is the collapse pressure. If your pressure at the bottom of the wellbore is below the collapse pressure, then the whole wellbore can fall into itself, right? This is what we don't want that. This is the minimum pressure that you always want to maintain. And the upper limit is given by the fracture pressure. So if your pressure at the bottom of the wellbore is more than the fracture pressure, then you're going to create fractures into the reservoir, and you will have loss of fluid, and consecutively it will drop the pressure because you're losing fluid. It's a unstable feedback loop, and it's a safety critical situation that you never want to touch on. So we always want this, the minimum and maximum is given by this particular constraints, and BHCP here means bottom hole circulating pressure. So it is not a static hydrodynamical head, but more of you account for the frictional losses as well. So generally there is a misconception to calculate the bottom pressure as a static head. What happens is if you calculate that particular pressure and you engineer your density of the mud, when you start the pump, there is an additional friction that acts against the bottom, and you might easily fracture the open formation. So you always have to keep in mind the frictional forces that are acting. So the bottom wall circulating pressure is the pressure that you will encounter at the bottom of the wellbore when you circulate the drilling mud, which is slightly higher than when your mud is not circulating. And there is another pressure gradient that is given by the pore pressure, which is nothing but the pressure at which the fluids are filled in the reservoir pores. And this is something that can vary. We don't have a natural trend. It's always an estimate, and we always take a informed decision and the best decision to avoid overpressure zones, because if your bottom hole pressure is less than the pore pressure, then you're creating a drawdown, and the fluid from the reservoir will flow into the wellbore. So these are the events when you have such unwanted flow. That's an influx. And if you cannot control an influx, then it will become a blowout. So of course you want to avoid such situations. Now let us see, now given that we have certain constraints, let us look at the pressure profile of the drilling mud inside the wellbore. You can see in the background that your drilling mud weight, the density is matching your pore pressure or slightly higher than that. And if you don't leave it, if you leave it open, then you're going to fracture this. So this is the point where you set a casing, and you can see this is an illustrative example where you have drilled into an over-pressured zone. So your pore pressure is higher than what the pressure encountered by your wellbore, right? So what you want to do is you want to try improve your or increase your bottom hole pressure from this particular point to the next point. And in conventional drilling, the only degree of freedom that we have is to change the density of the drilling mud and then start circulating from the top. If you do that, you can see that the pressure profile takes a linear shape and still given by this gradient. There could always be some section of the open reservoir where you are not able to manage the particular drawdown, and you will still have some influx from this region. This is a drawback in conventional drilling. And how could we now, dynamically manage such pressures? And if in a conventional drilling, then you might have to place another casing here to isolate the section, but that's an expensive process. So how could we widen this boundary and have a dynamic control? That's where managed pressure drilling comes in. What happens is, instead of having an open section at the surface flow, which is open to atmosphere, we isolate the circulation system using RCD, which is a rotating control device. What it does is it channels the flow from the annulus through a particular restriction. Here we have a choke valve. So when you have that, you can open or close this particular choke to dynamically control the pressure throughout the wellbore. In addition, you can also have another pump at the choke side that's called the back pressure pump. So you can even pump more fluid on the annular side should you need more pressure control. So as a combination from the choke pressure and the back pressure pump, if present, usually it is present, but we don't want to use it most often. So that's the surface pressure. So when that happens, instead of an open, instead of zero pressure here when it is open to atmosphere, we create a particular back pressure at the surface. What it does is, for the same density of mud, when you have additional surface pressure, it just gives a different pressure gradient, and you can successfully isolate this overburden section. Now you have controlled your influx. So this is very crucial. You don't have to go for a well-controlled situation where you have to close your BOP, expensive, time-consuming, but instead, just by having a restriction on the choke or having an additional pressure at the annular side, you can dynamically maintain a particular pressure or a required profile along the wellbore. So this is what is called as the managed pressure drilling operation. Now we will look at how to model such a system, right? Of course, the figure on the left-hand side is a schematic of how the actual system is present. You have your drill string that is concentrically placed on your annulus, and a section of reservoir that is open. You have varying diameter in the flow geometry because of your casing, etc. But it is too complex to model the realistic system mathematically. So what we generally do is we simplify the schematic into the formulation that I've shown you on the right-hand side. You can see that the mud pump supplies the drilling fluid, and it travels through a particular pipe with a constant area given by a drill string. And then this fluid experiences a pressure drop at the drill bit, and that's what is entering into the analysis, right? And we again assume we have a constant area for the fluid flow, and at the other boundary of analysis, you have a choke, which is nothing but you have another restriction for your flow. It's a choke valve, right, which you can operate. And to couple this particular wellbore dynamics with the reservoir influx, if you want to model kick situations and for well control, then you need a reservoir model. And we only need the reservoir model for the open section. We don't need the whole depth, but just the section that is in communication with the wellbore. So that's what is shown here. Now, I would like to point out that let us say, the left-hand side is the reality. And if you want to model, mathematically model such systems that's shown in the right-hand side, you're always going to miss out something, right? You can never accurately predict. Well, you cannot. It is not the reality. You cannot model a reality. You can only have an approximate representation of the reality, right? And the challenge here is how good your approximation. That's the key. You can have different types of modeling where everything is not everything is an approximation, but you can have different types of approximation. We will mainly look at a couple of methods to model such systems. And why do we need such models? Why do we need to model this fluid dynamics or the pressure dynamics inside such systems? Because the industry is facing a tighter pressure control problem where the wellbores that we have right now are having narrower drilling window. You're gonna drill deeper. You have more uncertain reservoir zones, so you need to have an accurate or tighter pressure control. And since you are drilling deeper and more uncertain situations, you have a high risk of having an influx. So you would also want to detect if there is a kick, and if so, you want to handle it better. And you want to do everything with a limited time because time is money. An additional important feature of this modeling process is reservoir characterization, which means that during the drilling process dynamically, you want to try understand what is the type of reservoir that you have, what is the porosity, what is the fluid that is flowing in, etc. So you then have to stop your drilling operation to carry out, for example, formation integrity test or drill stem test, etc. But you want to experience that or test the reservoir dynamically, right? So this was how can we estimate an influx using the measurements at the surface? So the topside measurement means the pressure at the choke, what is the fluid flow that we are pumping in, everything that is on the surface, right? Not an estimate of we don't have a measurement of bottom hole pressure, etc. So this was the focus of my PhD work. So this was the problem statement that we tried to address. If we can move to surface-based estimation and understand better dynamically during managed pressure drilling operation. So to do all this, we need a good wellbore reservoir model to understand the dynamics that is happening in, so that you have better understanding of what the pressure is in your wellbore, especially at the place where it is open to reservoir section. Because if you want to have real-time measurement of bottom hole pressure, then you need to have the downhole tools or using measurement while drilling operations or such things. This is highly prone to damage. Also, it is delayed. It is also affected by a lot of noise. So it's quite unreliable. And if you want to have better control, then you want to have a model that you can rely on, right? So as I initially said, you can always have an approximate representation of the reality. And one of the better approximation of the reality is using distributed dynamics, which is given by the partial differential equations, written as PDE here. It is a system of functions where each function is dependent on multiple states or multiple dynamics. So, and it's quite difficult to govern or model such systems. And the approximation just so ODE or the lumped dynamics is, as the name says, instead of distributing your dynamics throughout the flow path or throughout your system, you're lumping it into specific points or specific locations. So lumped dynamics is already an approximation of your distributed dynamics. So ODE here is the ordinary differential equation. You can always approximate a partial differential equation into an ODE, but since it is an approximation, you will always lose some of the dynamics. And this is the motivation of this particular talk. And we will go through how to create a model for the managed pressure drilling systems using lumped dynamics. But later we will also see simulations. Why, what are the dynamics that we lose when we approximate such systems, and what we could capture using PDE. Okay. Let's take a look at the derivation of such models. It is I'm going to first present a model that is already available in the literature. We famously call it as CASA model in the MPD community. Kosa, he's nothing but he's the one who heads the Kelda Drilling Controls company. I have attached his reference at the end, and yeah, he's the one who designed such simplified hydraulics model. So, as I said, since it is a representation of reality, we need to assume a lot of things. So the first assumption is we have a constant density throughout the drill string, throughout the annulus, and also in the reservoir. This is required to simplify our methodology. And as I mentioned earlier, we have a constant area, which means the drill string has a constant area and annulus has a different area that is continuous and constant, right? We don't have to, if you consider your tool joints and bottom hole assembly, then they are slightly bigger or smaller. So you don't want to have that variation. For this particular model, we're going to assume we only have a single pipe that is of constant area, and the same goes for annulus, right? Here we are only assuming a single phase fluid flow. Drill string, annulus, and the reservoir are filled with liquid. And also we assume that everything is at constant temperature. Sorry for the typo, it should be constant temperature. So we don't need to include the energy equation or thermodynamical balance. Okay. So in any of the system for fluid flow or etc., we are constrained by the physical laws, right? The first physical law is mass conservation, which translates into what you send in. The mass that goes in is the mass that comes out. If there is something that's going to retain, then that's the function given here. Whatever is accumulating inside your control volume is the difference between what goes in and what goes out. That's the mass balance. And here is the PDE, the general representation of mass balance. Here you can see that the density or the mass of the fluid that is accumulating at a particular period of time is given by its difference of the fluid flow. So when you differentiate it, then you have take the derivative, you take, well, we will come back to that. Okay, this is the general representation of the mass conservation in a distributed form. Now, if you integrate this particular equation over a control volume, right, with an area. So this particular volume has an area A, and the length or x goes from x1 to x2. For example, just take an example here as take the drill string as an example. If you consider this as the control volume, volume of this particular pipe is given by V, area A, and the x1 extends from top to bottom. When you integrate, you can get this function and you have a difference between what goes in and what comes out. Here, rho is the density of the fluid, v is the velocity that passes through this particular control volume. Now we know velocity can be given by q by a, where q is the volumetric flow rate, right? So substitute v in this previous equation, then you have constant a that comes out, multiplying a with this delta x. So area times length is volume, right? So you can get this particular mass balance equation where it's density times volume equals the fluid flow that goes in minus what comes out. This is the first step in understanding the mathematical modeling. The next step is just consider this equation, right? Now you want to apply chain rule for this derivative. Then you get a term in d rho by dt, and then you have dv by dt. What it means is this is a derivative of your volume. Here, if we are considering that, if you don't consider that you're drilling ahead, or if you're not adding a new pipe on the top, then your volume is not changing with respect to time. So we consider this particular derivative to 0 for simplicity. In reality, you're going to have some term here because you're drilling ahead, so you're continuously increasing your volume over time. This will become a function of your rate of penetration, ROP. Once you have that, you can already see we have some functions in density. And also we have some function in the density of fluid with respect to time. It's quite difficult to measure the density with respect to time or monitor it all the time at the surface. But what we could do is control the pressure, and it's much easier, right? So if you have to do that, we represent the density as a function of pressure that is shown here, that is given by the equation of state for liquid. This is an approximate representation of how your density will vary with respect to certain pressure. Here, rho 0 and P0 are the reference pressure and density. Beta is the bulk modulus of the liquid. So you get this differential equation. You substitute this particular equation in the previous one. You get mass balance equation. Now, if you recall, we have our assumption as constant density throughout the whole volume. So what goes in, what comes out, all the densities are equal. That is equal to rho 0, and that cancels out. So what you end up is a simplified approximation of your mass flow inside your drill string or any particular control volume. We have the mass conservation, and in the first principles of physics, we need to also have the momentum conservation, right? Here again, we consider constant density. Let us say this particular liquid is moving as a whole bulk mass. There's nothing fluid inside. It's just one particular mass that is flowing in together continuously. What you have here initially is the PDE representation of your momentum balance, which is nothing but some type of an acceleration term. Acceleration is equal to some of the it's the difference in the it's like a potential, how much the pressure difference you have. Higher the pressure difference, more your fluid will accelerate, right? And then you have some terms that is dependent on the frictional loss or the viscous forces, and you also need to consider gravity. Using the same formulation earlier, we can reduce this particular formulation to a simplified differential equation that takes this particular form. You see the fluid flow through a particular control volume is dependent on the pressure at the inlet and exit, the outlet, some frictional term, and some gravity. Okay, now we are finally at the coupled model, or when you want to show the dynamics inside the drill string and analyze using certain parameters that we can measure or control. Yeah, please remember that we have a mass balance equation and we have a momentum balance equation, right? In the first equation represents the mass balance for your drill string. The QP is the fluid flow at the pump, and Q bit is given by the flow through the drill bit. And the same goes for the annular region. You have the fluid flow that is coming in, that is Q bit, and whatever is coming out is QC. And remembering the momentum balance, we can represent this particular derivative, which is the pressure is the difference between what we have, what we pump at the pressure pump, and what we have at the choke end. And we have certain frictional terms. FDS is the frictional loss, frictional pressure loss using on the drill string side, and Fn is the function for annular side. You can see that the gravity terms have been cancelled out because for the gravity helps the fluid flow on drill string, and then it is against the fluid flow on drill string, so, in the annular side, sorry. So these terms will cancel out. M here is a representation of mass, which is given by this integral term. And if you're not aware of this particular notation, when you have a particular state and the dot on top, this actually represents the derivative with respect to time, right? So we have three states that governs the dynamics inside a drilling system. Now I present here an extension of the same system because there are a couple of shortcomings in the previous model, that is the COSA model. You don't have the pressure drop across a drill bit in the previous model, and you cannot include the reservoir dynamics into it. So what I present here is a work that I also covered during my PhD studies. So we first write the mass balance for the drill string alone. Now instead of representing qubit as an average of the pump flow and choke flow, we say it is only dependent on the fluid flow at the bottom of drill string. And the same goes to the annular region, which is now a function of QA. That's the fluid flow that is entering inside the annulus. Now, if you apply mass continuity equation at this particular boundary, you know that whatever fluid that is entering the annulus is that is it has come from the drill string and or from the reservoir. So your QA is a sum of both qubit and qres that is going into the annulus. And the choke flow at the right boundary is given by this particular equation. Kc is some constant, Zc is the choke opening, which is a function of T. This is the restriction we have on the choke valve, and we want to control this particular restriction to dynamically control our pressure profile. Pc is the choke pressure and P0 is the reference pressure. Now, to include the dynamics from the reservoir, you have to really be careful in the momentum balance equation. We write the momentum balance equation only for the drill string side. So now the fluid flow is a function of QD, that is at the bottom of the drill string. If you remember the mass balance equation, it is a difference between the pressure at the inlet and outlet. We have PP is the pressure at the pump and PD is the pressure at the bottom of the drill string, minus the frictional terms, that is the frictional function for the drill string, which is a function of the volumetric flow, plus we have the gravitational loss, right? That's given by rho g h. H is the length of this well bore. Now, please note, if you need to include the reservoir dynamics and the drill bit dynamics, then we represent PD as a function of the pressure loss from the annular side, right? So you want to come to this particular point, but you start from the right hand side. You start with the pressure at the choke, which is the surface pressure. Then if you come down to the bottom, you have the gravitational term. So the pressure at the bottom of the annulus is given by the surface pressure, that is choke. Then you have the hydrostatic head plus some frictional terms because of the fluid flow, right? That is also going to act towards the bottom of your wellbore. That's going to increase your bottom wall circulating pressure. And this particular frictional function is dependent on the fluid flow from the drill string and also the reservoir, right? And then you experience a pressure loss. When you come back to this point, you're going to cross this drill bit, right? Drill bit is particular. It's a particular valve like instruments, right? So you have a pressure drop. So if you jump from this side to this side, your pressure is going to increase, and that is given by this particular term. CD is some constant. AN is the area of nozzles. QD is again the flow through bit, and the gravity terms will cancel out. So this is the final equation that you will arrive at for the momentum balance. If you put everything together, now we have successfully integrated the flow from the reservoir that is given by QRS here. We have the choke equation. We also have the pressure loss across the drill bit. So the model that you see currently is the exact representation of how we could model the fluid flow in the schematic shown on the right. Please take a look at the terms in blue, QP and ZC. These are blue because of a particular reason. They are at the surface and we can control this, right? This is the input for this particular system. You can change the dynamics of all the states by changing your pump flow or by changing the opening of your choke valve. So this is the simple representation of MPD system, right? You can dynamically control your pressure using just by changing the restriction on choke valve. All right, so I'm gonna give us I'm gonna have a short pause here. So if you have any questions so far, is there any confusion before I proceed? You can just come out on mute and just ask me. Is there anyone present? Hello? Hello?
Yes, sir.
Okay, is there any question or something? Nothing so far?
No, sir.
Okay, I cannot see the comments, so let me know if there is any question or. Okay, so we will go ahead. I hope it is not boring, and I really believe that you're able to follow this. So we will now look into the distributed dynamics, but I will not jump on to the equations. Let's make it a little bit interesting, and I will show you some simulations about how we have the dynamics that is distributed throughout the wellbore, right? So let's see how to do that. I have set up a simulation for you guys, and let's see. Let me just.
Sir?
Yep.
I think we have a question in the chat box.
Okay.
It says, is there any specific tool used for modeling for NPD?
Specific tool as in the. Okay, let me just see. Well, what generally happens in the industry is we have different simulator and software solutions, but they are not open to the academia. They have proprietary softwares and proprietary simulation methods to model MPD. And killer drilling control is one of the example. They have some products called Stroma, which is a hydraulic simulator for managed pressure drilling operations. But what we have done is we in the academia, for example, we simulate this whole system in MATLAB or Python, and it is quite elaborate. So if you want to know more about how to model managed pressure drilling, the code base or the publications, and some of them are quite open. The code that we have created in this project is by rule from the European Union is open. So we can share with you about how to create a new simulator, etc. Right? Is that okay? Okay, there is one more. If we consider the reservoir dynamics for this model, shall we consider to be homogeneous or spatial variation of properties are taken into account? Right, as a simplified, so you can always do, you can keep on adding your complexities, right? What you have told is we generally have we make an assumption of a homogeneous reservoir model. That's just for simplicity, but of course it's not the reality, right? So you can relax this assumption, and naturally that will complicate your modeling process. What you want to always achieve is not to have a complex model, but have a simpler representation of the system, but still can account for these variations, right? If you have complex model that includes three-dimensional fluid flow, three-dimensional variation of your reservoir properties, it's just too complex, and that dynamics is not required when you apply in the real system. Some of the variations or heterogeneity doesn't even matter in the real life, right? So you can avoid certain these type of heterogeneities and assume that you have a homogeneous layer. We can I can show you in the presentation we have the modeling of reservoir model, and I also have some references that is attached, and I have some publications in the reservoir model and influx estimation, so you can have a look into it, and then we can discuss further if you want to improve upon it, right? So we are using ODE method to solve the equation, but there is not how much it can deviate in real life problems, right? So what we have seen so far is, as I just said, when you have a distributed dynamics, there are different dynamics at different time scale. For example, when you have a pressure variation, it just takes a few seconds to few minutes to affect or travel from the top to the bottom, right? But for example, if we have an influx and if we have the gas bubble that is transported into an annulus, then it will take few minutes to few hours for this particular dynamics and the propagation of these waves. So it depends on what type of dynamic that you want to model, or what is your importance for this particular system. So for example, it doesn't make a lot of difference when you model the system for the pressure wave for a single phase fluid using an ODE or a PDE. You will still have very close response. It doesn't deviate much. But for example, if you have a gas influx and if you model it using an ODE, then you're going to deviate too much from the reality. And that is when you need the distributed dynamics to have better understanding of how the gas propagates and control it.